Hello, my name is Liam Christianson, and this project models how water drains from a system after a rainfall event using differential equations. The goal of this project was to determine whether an initial value problem could accurately model drainage behavior over time. I would also like to really thank my professor for guiding me in the right direction because I was almost lost with this project, and they really gave me some good guidance. So I wanted to go over a quick content overview. I wanted to go over the problem, why it matters, my experimental setup, my mathematical and differential equational models, the results I got, and my conclusion and reasoning for this. So moving on to the introduction, drainage systems are important for preventing flooding, erosion, and water buildup after storms. In real drainage systems, water depth changes continuously over time as the system drains. Differential equations are useful because they can use these models to find the rates of change in systems like this. So I wanted to go over the weathers and values that I used to find the numbers for this project for proper drainage systems. I went to April 1st of 2026 in the Rapid City, and I used the Rapid City Regional Airport as a standard proxy to find all the precipitation. And by using NCDC, NOAA.gov, they gave me some good graphs and some good information to continue further on this project. So moving on to the experimental design, I used a simplified container like this instead of a real drainage because it allowed for controlled measurements and repeatable trials. The cube shaped also created a uniform geometry, which really helped simplify the mathematical modeling of this process. So going to the experimental setup, I used a 10 by 10 by 10 centimeter cube container filled with water to an initial height of 10 centimeters. So let's just say this is 10 centimeters, and I had a drain at the bottom so I could use a ruler and timer to measure the water depth every minute that was pouring out of that container. And to simulate the rainfall, this water was used and added at a controlled rate based on the precipitation estimates from April 1st of Rapid City. So I conducted a total of 10 trials to improve the accuracy and consistency of this project. The water height was recorded every minute until the system was nearly drained, so some trials were simulated post-rainfall drainage without additional rainfall, while later this trial included a rainfall input term. So moving on to my exponential decay model of the first differential equation, I use dH over dt by negative kh. This first model will assume that the drainage rate is proportional to the current water depth. So this will produce an exponential decay model, meaning the system drains quickly at first and then slows down over time. Although this is called a no-rain model, it'll still represent a rainfall event because it models the drainage process, while after rainfall has already been stopped. So here's my solution to it, initial value h by e to the negative power of kt, and then my variables. Moving on to the second model, which is a more realistic rainfall model for rainfall downpour. The second model adds a rainfall term to represent the continued precipitation during a drainage point. The rainfall input slows the decay process and changes the long-term behavior of the system. Instead of draining completely down to zero, this system approaches a small, steady, but yet state depth. So moving on to my parameter estimation of this project, the exponential data that I used to estimate the constant drainage K was by using multiple trials and logarithmic calculations. So by using this formula and having multiple trials and putting that all together through the equations, the average value that I found was 0.131 for the approximation. And then this value was then used to build my final IVP models. So for my final IVP models and using the average value of K, I constructed the two final values that you can see right here. This first model represents the post-rainfall drainage, while the second includes a second rainfall input right here. So both models follow the overall trend of the experimental data, and I want to explain why no rainfall matters. The no rain trial represents the drainage behavior after a rainfall event has already been filled to that system, meaning in real drainage systems, water continuously drains even after rainfall stops. Therefore, this exponential decay model describes the post-rainfall water loss. So moving on to my graphs right here, we have no rain, numbers off to the side, with rain, numbers off to the side, and then with exponential rain, numbers off to the side. As you can see right here on all of them, on the green and orange, these graphs compare the experimental data with the theoretical models. So these rainfall models also show how continuous inflow slows the drainage results. And with this and combining all these together, I have seen that with the exponential decay model and realistic rainfall equations, they are very similar in curves, which means by these mathematical models, they're pretty spot on from what I've gotten so far. So moving on to the analysis and limitations of this project, the models were effective because exponential decay naturally describes many drainage systems. This real drainage systems are more complex, but the simplified model still produces accurate overall behavior. Moving on to the weaknesses and limitations, I had a lot of measurement inaccuracies, but by using simplified geometry and the assumptions of this project, I was able to get a constant rainfall. And then moving on to this conclusion, overall, this project was a lot of fun, and this project demonstrated the differential equations that can successfully model real-world drainage systems. Even with the simplified assumptions and discrete measurements, the models closely match the experimental data of which I used. And this project showed how mathematical modeling can be used to get a better understanding of physical systems and environmental processes. So, thank you for listening through my PowerPoint and my YouTube video. I really hope you learned something new from this, and you all have a fantastic day.